writing what we did last lecture. So I recall you that we were studying a sub-Riemannian manifold that at this level we can think just to an optimal control problem linearly controlled with some bracket generated vector fields. And now we are taking an external volume, so later on we will extract the volume from the manifold. And we have defined the sub-Riemannian Laplacian, that I called also sometimes delta H horizontal Laplacian, the divergence with respect to the volume of the sub-Riemannian gradient, and we have this nice formula, so we get this operator, it is the sum of the square of the vector field as operator on function, plus some first order term that depends on the volume. So now we would like to study the heat equation, indeed, studying diffusion. And so now we use this very powerful theorem of Ormander that says that if we have a set of vector fields that are bracket generated, and if I consider an operator that is the sum of the square of, so there is one vector field that is the drift, and so that is not square, just applied directly, and the other applied twice, then this operator, it is hyperelliptic, and so this means that if you have that the application of the operator on the function, here you will think to a distribution, so if you know that this after this operation you get a C-infinity function on an open set, then the function equals originally C-infinity. So this kind of inverse way of seeing smoothness, and now we see how, so we already saw how to use this. So the theorem of Ormander, we can apply both to the sub-Riemannian Laplacian, so in this case, since we have that this part is the bracket generated, y0 will be simply the drift, and so this is hyperelliptic, and will be hyperelliptic also the heat operator, so minus dt minus delta sub-Riemannian, so because now y0 will be the same term as before, but also with delta t, because these are generating all the spatial directions, and this part is generating the direction t. So both the operators are indeed hyperelliptic. So this is the crucial point. Well, so now one would like to use this theorem to prove that the solutions are smooth, but you have to guarantee that at least a solution exists of this equation in distributional sense. So because we are studying the equation, so dt minus delta sub-Riemannian phi equal to 0, so 0 is infinity, and so if I have a solution of this in distributional sense, this theorem will tell that the solution is smooth. So to prove the existence of one of the solutions, we use a theorem of Strigart's that says that if the sub-Riemannian manifold is complete, so as a metric space, then the sub-Riemannian Laplacian is essentially self-adjoint. So we discussed what does it mean, but in practice this means that there is a unique solution, so you can use the theory of evolution equation in L2, and you have a unique solution of the Cauchy problem. So in 0 infinity times L2, so here you see appearing the volume that we have chosen, and so be careful. So here I put 0. So this is the evolution equation. So the solution will exist starting from 0. So now I know the existence of a solution in L2. So this is not written correctly. directly, of course. So this will exist in L2, and will be defined in 0. Will be defined in 0 infinity times m. So considering also the time, and since since this solution exists in distributional sense, I have automatically this solution, it is smooth. So be careful that the smooth, now I will have it in the open interval, not in the closed interval, because this theorem requires that this is smooth on an open interval. And so even if here the solution I have it on the also including 0, then I will be smooth with 0 outside. And so this is obvious, because you know that you can start, usually what you do, you start with a Dirac delta at a point, and then you make the evolution, and Dirac delta is not smooth, but will be smooth immediately after. When you make the fundamental solution of the equation, you start with a Dirac delta. You have this theorem hold, so you have a solution exist unique in 0 infinity times m, but the solution will be smooth after time 0. Of course, at time 0 it is just a distribution. So this is open now. Okay. So we have seen last time that if we don't have the Ormander condition, and we have, for instance, this vector field define a foliation, so you cannot move from a different sheet of the foliation, then of course you will not have a theorem like this, and if you start with kind of singularity on a different sheet of the foliation, you will propagate it also after. So this Ormander condition, it is important to mix the different components. And so we also see why it is important to be complete, because if we are not complete as metric space, we don't expect to have the theory holding, because I already said several times, we consider just R2 with the standard Riemannian structure. I consider my heat equation defined on a disk. And so, of course, this theorem it is not true, because I have to be able to define a unique evolution, I should specify some boundary condition. So specifying a boundary condition, it is equivalent to specifying one of these self-adjoint extensions. So the Laplacian on the disk is not essentially self-adjoint, means that there are several self-adjoint extensions, and to each of them will correspond certain boundary condition that you have here. Instead, if you are geodesically complete, the fact that you are working L2 means that you don't need, at infinity, you don't need additional boundary condition. Okay. So, just one remark. So, sub-Riemannian manifold complete means that the sub-Riemannian Laplacian is essentially self-adjoint. So, the opposite. This is anyway is not true. And today, later on, I will show an example of a situation in which the sub-Riemannian Laplacian is essentially self-adjoint, but the manifold is not complete. So this is not a very common situation, but also is not pathological. So with this I would like to discuss later. So this is something that is important, in my opinion. Okay, so this is what essentially we saw last time. And now I would like to discuss the next point. So next point is, so we we have several things to say now. So there are some fundamental questions that we are interesting for mathematicians for several years. So the first one is finding a relation between pt of xy. So I have to say to you what is pt of xy that I forgot now, and the sub-Riemannian distance. So I should add one small theorem that is still due to Strickhardt, that says that so sub-Riemannian manifold complete. So we have exist. So delta is essentially self-adjoint. So we have a unique solution of this. So we have also that there exists a smooth positive heat kernel. Smooth, positive, and symmetric. So this means that you can write the solution of this as phi of t x as the convolution. So you integrate on your manifold a function that is smooth, symmetric, and positive, and then you make a convolution with your initial condition. Okay, so this is more or less a simple consequence of what is happening before. So you have that your solution is smooth, and also, thanks to Ormander, you can express it as the convolution of the initial condition. So this one, so it was q there, now it's y, okay. The convolution of a function with phi 0. And of course you should interpret this, you can interpret this as initial condition, because if you put here a Dirac delta, so if phi 0 of y is equal to delta of y, then you get that phi of t x is equal to pt of xy. So pt indeed is a solution of the heat equation starting with initial condition at Dirac delta. So the idea is that on your manifold, if you put a Dirac delta here, and then if you want to compute, so the heat kernel gives you how this is evolving on the manifold. Okay, so the question here is to relate Pt, so this heat kernel, with the distance. So one would like to relate this, and also what is the role of omega, because you see that this is independent on omega. This is the sub-Riemannian distance, and this depends on omega. So this depends on omega simply by definition, because this dy, of course, is the omega y. So I'm integrating on the manifold with my volume. So the first question is this one. So the second question is how to get explicit expression. Over Pt of xy. So Pt of xy is essentially the solution. So once you have this, you compute by convolution the solution with any and then that was an initial condition, and then I would like to know, so is it possible to get omega intrinsically from the sub-Riemannian manifold. Because this would permit to kind of understanding, so having a heat equation that is really intrinsic, that depends just on the sub-Riemannian structure. So this would be the goal. So now, in the remaining of this lecture and in the next lecture, we are going to answer and discuss how to get some idea how to answer to these questions. So, okay. Now I would like to discuss together a little these two questions. And so I will, first of all, try to get some expression of this in some easy cases. Let's get expression of the heat kernel in some easy cases. So let me, everybody knows how to get the heat kernel in Rn, so in the Euclidean space. So that is very easy. So I would like just very briefly to repeat how to do, because then we will have to do kind of similar things in a sub-Riemannian case. So how to solve this equation? So we have dt minus dx1 square plus dxn square phi equal to 0. So we would like to solve this equation. So there are many methods to do this. So the first idea is to go to make the Fourier transform. So you go in Fourier in the variable x, and so you get that dxi so will become a multiplication for the dual variable, and so this equation become dt plus lambda 1 square plus lambda n square the Fourier transform of phi, so now with the function of t and lambda, so equal to 0. So that it is very nice because on lambda we have no derivative, so this is just an ordinary differential equation. And so we can write the solution in Fourier transform, and so we have that phi of t lambda will be equal yes, so there is my I that is the same xj. And so now this has immediately solution. It is just an exponential, because this is a family of ODE, so we have some initial condition phi0 of phi0 of lambda, and then it is e to the minus, so lambda 1 square plus lambda n square times 2. Okay, so this is simply the solution in Fourier transform. So now we write this, so the initial condition in lambda as the Fourier transform of the initial condition in x. So I will write this as the integral from minus infinity to infinity of phi0 of x e to the minus e lambda x in dx. Sorry, I will write not x but y because I will write y, so this is already another variable. Okay, so this is the solution, and then we make inverse Fourier transform. So now we make inverse Fourier transform, and we get that phi of x t, so the inverse Fourier transform will be 1 over 2 pi to the power n, and then the integral from minus infinity to infinity of phi hat of lambda t, with the inverse of this, that will be e to the I lambda x in dx. Make the inverse. And so now everything is working very well. So we have two integral, one in x and one in, sorry, it is integrated in lambda. So it is integrated in lambda. I should make lambda is appearing, make appearing x. And so you get 1 over 2 pi to the power n. And then I will write the integral of phi0 of y, and then I have everything that remaining inside, so the integral from, so also minus infinity to infinity of, so let me take all pieces, so of e to the minus lambda 1 square plus lambda n square t, and then e to the this term and this term, e to the e lambda, that's x minus y in d lambda, and then in dy. So in principle I have all terms. And so now things are working very well, since this is a Gaussian. The Fourier transform of a Gaussian is still a Gaussian, so we have just to put in order the constants. And then we get the nice expression. So this will be, of course, what I was looking for. So this will be pt of xy. I'm writing the solution in x by making convolution with pt of xy, and then we get the formula. This is just what is called the Gaussian kernel, and then so the final expression I will write correctly. So pt in Rn, pt of xy, it is simply 1 over 4 pi t to the n divided by 2. So this t comes from yes, from this t here. Of course, here there is also a t, also a t, and then e to the minus, and then we get the norm of x minus y square divided by 14. So very nice. That's So it is interesting to notice, so now we make a digression of 1 minute. So all this looks really magic. So you see that why it's working so well in this case, so indeed, this is magic because the Fourier transform by definition. So this object here, so this transformation, it is created to transform well the derivative with respect to the coordinates. So the Fourier transform, it is an object that transforms well the left invariant vector field on a group. So in Rn, we are, so the derivative are indeed the derivative with respect to the coordinates are indeed the left invariant vector fields of this very simple group that is Rn with the sum. So with the abelian group Rn. And indeed, this object here are these are the representation. These are the irreducible representation of Rn plus. So the Fourier transform, indeed, so this is not really magic, but it's due to the fact that the equation, so this equation is linear, it is equation written with invariant, left invariant vector field on this very simple group, and the Fourier transform, it is built, I think that at the time Fourier didn't know this, but what you put here are really the representation of the group, and everything is working for this reason. And all this can be generalized to many other groups. So you can build, if you write a heat equation on another group, for instance, on the group of rotations, or on the group, indeed in most of groups, you have a theory that is very similar to this one. Things become more complicated, but the concept is the same, and you will be able to transform well, so to reduce a number of variables of an equation that is built with the left invariant vector field. So that is very interesting story, of which now I cannot say much, but the first time in which the heat kernel for the Heisenberg group was built was exactly by doing this. So using a Fourier transform of the group to transform the heat equation that is on the Heisenberg group written with this left invariant vector fields in a simpler equation. Okay. So, but this is a digression that I wanted just to tell you that each time that you would like to study a PDE that is linear, that is built with left invariant vector field on any groups, you have very, very powerful techniques. So this is called the non-commutative Fourier transform. A fundamental tool to study PDE on only groups. Okay. So now I will stop with this digression, and so we are now seeing that this object here. So I come back on Rn. So I'm just studying this simple things. So this x minus 1. This is precisely the distance square between x and y. So we have the following. So pt of xx is equal. So this is called on the diagonal. So the heat kernel on the diagonal when you put really the same value here. So you're looking how the heat is going down when you start with a Dirac delta. So this formula gives us the result. So x is equal to y, so the term is equal to 1. And so you get a constant divided by t to the n divided by 2. So this is an Euclidean space. If you put a Dirac delta in Rn in a point and then you make evolution with the heat, this will go down as a polynomial, as 1 over t to the n divided by 2. Okay. And so this is on the diagonal, so out of the diagonal, so I will write, so this is on the diagonal, so, and out of the diagonal, so I think we have the same formula, so I get out of the diagonal that dt of xy, let me just write as some constant divided to t to the n divided by 2, and then we have this very strong factor xy squared divided by 14. So this is out of the diagonal. So this is in the Euclidean space, and this we computed. So now let's see what is true in what is known in Riemannian geometry. So in Riemannian geometry, things are not very different. So on the diagonal, so you take any Riemannian manifold. So on the diagonal, you have that pt of xx. So this is precisely. So this is equal to c plus small log of 1, so some higher order term, and then divided by t to the n divided by 2. So in Riemannian geometry, you have an expression that is similar to this at the lowest possible voltage. Okay? And so this is all the result of this is, I don't know how to write this Indian guy. And this is in 49, so this is all the result. They studied also higher order term and getting information on the curvature of that. But now we are just interested to the lowest possible term. So, and if you are out of the diagonal, then there are two cases. So out of the diagonal, there is the case in all points. You have that the log of pt of xy tends for t that tends to 0, so this is a rough estimate, to e to the minus the distance square between x and y divided by 4t. So this is a result much more, sorry, so this is Varadhan. I think it should be 77. So this is, says that you see that out of the diagonal you have always this kind of term here. So this stated, of course, you compute the logarithm on this side and on this side. So the limit, this will be killed because this go to 0 much more. So this is killing this. So if you compute the logarithm, you get logarithm of this is killed, and you get just logarithm. Yes. Without being, yes. Thanks to this.
It's also Indian geometry.
Sorry? I don't know. He's in the United States. He was in Columbia, New York. He's still there, so I don't know where he's coming from. The name look, but okay. So make a small review of the results that are known in the Riemannian context, and then so there are some more precise. I want to like to know more precisely if there is something in front, because this says you that the leading term it is still an exponential, and so there is a result of Benarus of 91 that says that out of cat locus, so cat locus we saw where geodesic lose optimality, then he has an expansion that is as in the Euclidean case, so e to the n divided by 2 e to the minus the distance square xy divided by 14. So the leading term, so you have the right exponential beside this constant that will be, then we have some other term, but the leading term is precisely the same. And so on cat locus, Riemannian, so on cat locus situation it is different, and we have that the expansion is of this kind, t to the power alpha, e to the minus d square xy divided by 14, and we have that alpha it is bigger or equal than n divided by 2, and depending we write like this on the structure of optimal geodesic. And so this is very recent result by Ming and myself of I don't know, 2 years ago. Maybe it was in 2014 it was published. Okay, so this is essentially what. So here one can know precisely how. So if you know really the structure of optimal geodesics, you can give the precise value of this alpha, and indeed it depends on how many geodesics are arriving to the point, because you should imagine that for a small time the heat is essentially traveling along geodesics, and then if you have more geodesic for a small time, you will have more heat, and so you will get a power here higher. That you will go, so you have more heat appearing.
Excuse me, so this was more for Riemannian case?
This is Riemannian, yes. This is Riemannian, and I will discuss for sub-Riemannian later. Okay, so maybe we can make a break now, and then in the second part of the lecture I would like to show you how to compute easily the heat kernel of the simplest sub-Riemannian structure that one can construct, that is the Heisenberg group, that plays the role essentially of this Euclidean case. So we will, I will not make all computation, but I will give you the instruction to, let's say, to compute it. It's not very complicated. And so we will write the expression, and we will go to see how much is on the diagonal, how much is outside the diagonal, and then I will give you some results that are known in the general case. And then we will see that some interesting things are appearing. And then once that this is done, we start to discuss the intrinsic form. I would like to do something very similar of what we did in the Euclidean context for the simplest sub-Riemannian structure, and so we take the Heisenberg group. So I take the Heisenberg group. So the Heisenberg group it is R3. And my two vector fields are one is this one, and the second one is 0. So 1x divided by 2. Okay, so still we don't know how to have an intrinsic volume from this. And so to build the heat equation, I will need to take an external volume, and so I take the external volume dx, ui, dz. So this will be the Lebesgue volume given from outside. And then I would like to write the sub-Riemannian Laplacian. So let's call this f1. So this f2. So I will have f1 square plus f2 square. Plus, so the divergence with respect to this volume of f1 times f1 plus the divergence with respect to omega of f2 times f2. Okay, so let's compute this. So what is the divergence of f1? So since this volume is the standard volume, divergence is the standard divergence, so I have to take the derivative of first component with respect to x, so 0, derivative of second component with respect to y, 0, and derivative of the third component with respect to z, 0, and I should sum them. So the standard divergence. So this is 0. So the divergence of the first vector field is 0, and also the divergence of the second. Great, so no first order term. And so this sub-Riemannian Laplacian, it is, so now I write as operator on function, so dx minus y over 2 dz square plus dy plus x over 2 dz square. Okay, and so this is the operator that we have to start with. So now question about completeness. So I will not discuss this, but this is in this case, so this is implied by one can prove using that vector field sub-Riemannian. So indeed, if you want to add just one third vector field 1, 0, 0, and this become a Riemannian metric, this will be complete because these vector fields are sub-linear. So I would not want to discuss now this. It is easy to prove. And then we would like to study. So now my goal is to build the heat kernel for the equation dt phi equal to delta sub-Riemannian phi. So now you understand that a situation it is more complicated than before, than the standard Euclidean case, so because we have more variable, so we are not just one, or it was in Rn in that case, so it's not more variable than before, but the difficulty is that variables are more coupled one to the other one, but still it is not hard to find this heat kernel, and now I will explain you how to do, even if I will not do all details, but that will be a serious. You understand why we can. So the first step, we make a change of variable, and I will send z in a variable w that is defined as z plus 1/2 xy. So if you do this, so the vector fields in the new variable, so x1 that we still call x1 will become 1, 0, 0, and x2 will become 0, 1, x, just by making this change of value. So for those of you that know the Heisenberg group as a group of matrices, so this change of coordinates corresponds to go from coordinate of the first kind to coordinate of the second kind. So this is just this, it is just this, but it is not important. So you make this change of coordinates on the vector fields, and then the vector field becomes more simple. So this is the other representation of the Heisenberg group. In books, sometimes you find in this form, that is symmetric by rotation, and sometimes you find in this form that is not symmetric by rotation, but depends on less variable. So okay, so now we write a heat equation for this. So I will have dt phi equal to dx square plus dy plus x dz square phi. And now phi of so the old capital phi, which was function of x, y, and z, so will be phi of x, y, small phi, and w, that is z plus 1/2 xy. So this will be used then to come back. So well, now step 2. You see that now we can make a Fourier transform. I will make a Fourier transform in two variables. That are not appearing, so that appear just in the coordinates. So x I cannot transform because of multiplication by x. If I transform, become a derivative, and I don't get nothing. So we transform y. So indeed I will transform dy, that will become e mu, and I will transform dz. So again, z is not appearing, so we are just the derivative, and this will become e ni. And so now my equation, it is simpler because it is dt phi, the Fourier transform, so it will be equal d2x, so now minus, that comes from I, so I have mu square plus x, sorry, mu plus x, ni square, yes, great, phi hat, and phi hat is the Fourier transform. So you see that is very, very good, because now this is a PDE, it's still a PDE unfortunately, but in T and X. So mu and nu are two parameters. So my PDE that originally was in X, Y, Z and T, so now it is just in T and X. Okay, so now we make another change of coordinates. So I will call, so we make the change of coordinates X that become theta, where theta is defined in the following way. So we call this object here nu times theta. Oh, just I would like, of course here there are a lot of parameters, I can just get one bit less. And so at the end I will have that my equation becomes dt, so phi now I call phi bar, because now I have again changed the name. So phi hat over x mu and phi will be this phi bar of x, so of theta over nu and x, and then phi bar depends on depends not on mu anymore, depends on me and on t. Okay, and so my equation now it is d2x minus mi square theta square, sorry, d theta. No, I'm right. Yes, this one times phi bar. Yes. Yes, there's some simplification to do. This is what you put here. Yeah, because we have mi x, mi theta, so this part remains the same because they are multiplied by the same. Yes, so that's correct. And so now you understand that this equation it is much more easy than before, because now this is really a PDE in just one variable, and who of you that saw some quantum mechanics in their life will recognize that this is almost the quantum harmonic oscillator. So this is the quantum harmonic oscillator. With no I. So it's the quantum harmonic oscillator without the complex, it is not the Schrödinger equation, but it is the heat equation. And so this can be solved. So this it can be solved in terms in Hermite polynomials. I think that also on the probably also on Kolmogorov forming you find all these Hermite polynomials that permit you to solve it, and you can also get really the kernel of this. And this is called the Meller in a similar way of how we did in the Euclidean case, but computations are much more complicated. And by doing this, so this is just the instruction to compute, you get that the explicit formula that I will write here of x, y, z. So I'm coming back, of course, to the full set of all variables, and I get the following expression: 2 pi t square integral from minus infinity plus infinity of 2 tau, and then the sinus hyperbolic of 2 tau, and then you have the exponential. So this is not completely explicit, but almost. So it is written as Fourier transform of an explicit function. So we have x minus x bar square plus y minus y bar square divided by 2t, the hyperbolic tangent of 2 tau. And so this is Fourier transform, so I have still to multiply by a factor, oscillating factor, which is cosinus. So this is written just with a real variable divided by t in the tau. So it's a long expression, but it is the simplest expression of the heat kernel in sub-Riemannian geometry. So when so this formula was obtained in 76, 77, 77 by Gavot, with in France, with a very, I don't know, mysterious method, and was obtained by Hulanicki. I don't know exactly how it's written, as a Polish guy. Hulanicki, the same year, more or less. So they were working at the same time. He published, I think, 1 year later, so he became famous and he not. But the method of Hulanicki is by non-commutative Fourier transform. And the method of Gavot is completely different. But you see that now I don't know why it was so hard, but this was a great achievement and considered a very hard problem. So today, you know, make just a couple of Fourier transform and you get the result. With no use of any complicated tools. You just make Fourier transform into variables and then that's done. But this was the starting point of diffusion in sub-Riemannian geometry, because this gave the first, let's say, hint of what was the behavior of the diffusion on this degenerate Riemannian manifold. So, okay, so now let's see what it gives. So on the diagonal, so we do what we did in the Euclidean context. So on the diagonal means that you are in the same point here, y and z. So all this will be killed, this will be killed, and you remain with the integral of some function that is this is finite. And so on the diagonal you get just a constant divided by t squared. So the square, the t square is just the rest is just it becomes just a constant. So first interesting story. So these two, so this is not n divided by 2. Because n divided by 2 would be 3/2. So you already see that in sub-Riemannian geometry, even on the diagonal, the point, the behavior of the heat is quite different, and we will discuss why. So let's go on other points. Then you have on the z-axis. So you take this formula, you compute this integral on the z-axis. So z-axis, I mean, z-axis. Okay, let's write the z-axis, but I mean pt of 0, 0, z, 0, 0, 0. Okay, we start from the origin, and then you compute this. This you can compute explicitly, so it is a little more complicated integral, but this is doable, and you get c divided by t square. T square is still there, and then you get an exponential factor that is precisely the distance square between 0, 0, 0, 0, 0, z and 0, 0, 0 divided by 4t. So great, so we see coming some geometric object, the distance, and out of the z-axis so I mean p of course the second point is not very important because the structure is invariant by certain translation, so this you understand when you write this as a group, so we are not done. So in the other point, I mean x on x, y, z, and 0, 0, 0, always with z different from 0. And on all other points, you get, so this is more hard to compute, this integral, this possible, this explicit expression, and you get e to the minus the distance square between this point, x, y, z, 0, 0, 0, divided by 40, 3 divided by half, 3 divided by 2. Okay. Okay, so that was the first in the 70s. People end of 70s understood this kind of thing. So they saw that there was some strange behavior. So on the diagonal, this is not n divided by 2. So this out of the diagonal is not n divided by 2. And when you are out of the z-axis, you have n divided by 2. So this is n divided by 2. Okay. So now I will just give you, we'll just say you what is known in sub-Riemannian geometry for general structure. So on the diagonal, so this is a general sub-Riemannian manifold, and you and omega is a smooth volume given from outside. So on the diagonal, it is known that pt of xx, this is equal to c plus o of 1 divided t to the power q. So q is not n divided by 2, but this is the Hausdorff dimension. Of the manifold, let's say F2. So I will tell you later. So sub-Riemannian manifold is a metric space. So we can compute its Hausdorff dimension. I will give you the definition later on. And what happens is that here what you have to put is not the topological dimension, but the metric dimension of your manifold. Yes, general sub-Riemannian manifold, smooth volume and non-normal. Non-normal trajectories, otherwise all this is not true. So
is a Hausdorff dimension. What does it mean at Q?
At Q, yes, it's unfortunately the Hausdorff dimension of a sub-Riemannian manifold can change with the point.
You mean at X?
Yes. Sorry. Yes, at X. Yes. 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 Certainly. So so in all points we have the same formula than Riemannian. So the log of pt over xy tends to minus d squared divided by 14, and so this is Leandre. So this is precisely the same result of the Riemannian case, and d squared divided by 4t, d squared over xy, and this is 89. And then out of cat locus, the same expression than the Riemannian one. So this is like I will write R here, like the Riemannian one. This is like the Riemannian one. So t to the n divided by 2 e to the minus the distance square of xy divided by 14. And then on the cat locus, so this is again more or less like in the Riemannian case. So c plus o of 1 divided by t to some power alpha e to the minus distance square of xy divided by 14, and so alpha it is bigger or equal than n divided by 2, and again depending on the structure.
So there Q must be divided by 2, yes, on the very first formula, or no?
Yes.
So Hausdorff dimension of Heisenberg is 4, yes?
Yes, thank you very much. So this is divided by 2. Yes. This is divided by 2. Thank you very much. Okay. So, well, now I would like just to
For any sub-Riemannian structure.
Sorry?
It is true for any sub-Riemannian structure.
So this is true for any sub-Riemannian structure where there are not normal.
There's no.
Not normal. So open question. Open question. So what happened with abnormal? Okay, this is not normal. So let me just now make your understanding. So why on the Heisenberg group so why on the Heisenberg group Q is equal to 4. So this is so we not prove this, but it's not hard to understand. So what is the Hausdorff dimension? So we call it S because I'm going to define the spherical Hausdorff dimension, Hausdorff measure. So this is defined the following way in a general metric space. So you are in a metric space MD. You have a set omega, any set containing M. So you take your set omega, and then you cover by balls. In the sub-Riemannian case, you cover by balls that would be like this. So you should cover well, and then you take so all balls of a certain radius, you take the best covering, and then you send the radius of balls to 0. And then you sum all what you get. So it is the limit for delta that tends to 0 of the infimum, so the best covering. So there is some constant that now I will not fix. So you make the sum from of epsilon, so sorry, delta to the power s. I'm defining the s Hausdorff measure. Such that sums over I, and then you should take your your omega should be inside the union of some balls centered in some point xi and of radius epsilon. So what you do, you take your set, you cover with balls of radius epsilon, and then you sum the measure of these balls with different power. So if you do this in a Rn and you want to measure a volume, you should put 3 here. If you want to measure surface, you have to put 2. So what is interesting it is that if you here you have a S, so the power that you put there, and here you have the measure S of power S. So this is always infinite, then it becomes 0, so here infinite, and then when it's changing from 0 to infinite, so you can prove it is always like that, this value it is the Hausdorff dimension. So it's the only value of S for which by doing this operation you get something that is either finite, either infinite, but on the boundary between the two. Okay. So if you do this with in Rn, in R3, for instance, you want to measure an open set. So here you should put 3 because the volume of the balls is go like the radius and the power 3. But you can measure the set made very directly. So now why the Hausdorff dimension of Heisenberg it is not equal to the topological dimension, it's not equal to 3. So the reason it is the following is that you take well, just give an idea of how you do. So you take an open set and you try to cover this set with some balls, with some Heisenberg balls, and then you know that on two sides, if you take balls of radius epsilon, here you will go with epsilon, here we'll go with epsilon square. So if I refine now, I take a covering, and then I would like to refine, so I take radius epsilon and I send to epsilon divided by 2. So since here I have then to send, so this was not delta, of course, it was epsilon. So I should take the best.
Another place also epsilon.
Ah, thank you. So thank you very much. So now now if I take epsilon divided become epsilon over 2, so how many balls I have to put more? So I have so on this side, if you divide by 2, you should put 2 balls. But on this other side, you should put 4 because this go with epsilon to the power 4. So if I divide by 2, I need how many balls? 2 times 2 for this direction and times 4 on the other side. So and this is 16. So now when you do this operation here, so you want something that when you send epsilon to 0 will not go neither to infinity neither to 0, and so you should get something, some constant, and then you have so you should get something like this. So if you want that this so when you divide again this number go neither to 0 neither to infinity, you should put that s is equal to 4. Okay, so this is more or less the idea. Essentially, the Hausdorff dimension tell you how many balls you have to put when you refine your set. So, and due to the fact that the balls has some different so epsilon to 0 on one side go like in Euclidean space, and other side differently. This make the Hausdorff dimension bigger. So there is a formula I did due to Mitchell that say that for equiregular sub-Riemannian structure, you have that the Hausdorff dimension it is equal to the sum from 1 to k equal to the step of the structure of I times the dimension of di minus the dimension of di minus 1. So and here equal to D, your distribution, equal so D2 equal to D plus D1, D1, and so on. And so you can compute, and you say that it's equiregular when the dimension of these spaces that you get by adding bracket is not changing with the pole. So equiregular if dimension of the I is equal to constant. Okay, so this formula permits you to compute Gaussian dimension. In the case of Heisenberg, so the dimension you have to sum k is equal to 2, so that you have one that multiplies, so the first one has dimension 2, the other one is 0, does not exist, plus 2, and then the dimension of the third, so with one bracket you get the full dimension of the space, so you get 3 minus the dimension of the one before 2, and so you get 4. This is the formula. Okay. So I think we can stop here for today. So our next lecture will be the last one. Not to do still many things, but okay, we will do a certain number of things. So I would like, so one compromise for a long time, so to discuss how to get a volume from the structure. And I would like to show you that in many interesting cases, indeed, that are the cases that are not equiregular, for instance. So this volume, it is singular, and so this will make this sub-Riemannian Laplacian becoming singular somewhere, and will have very interesting feature. So up to now, all what we said, it was with a smooth volume given from outside. And we will see that if the volume it is given by the structure itself, so in the equiregular cases, we will be able to build a volume that is smooth and will permit to build a good sub-Riemannian Laplacian. And if the structure is not equiregular, then this volume will have some singularities, and then this will create some additional interesting phenomena.